Chapter 6 of Is Mars Habitable? This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. Is Mars Habitable? By Russel Wallace. Chapter 6. A New Estimate of the Temperature of Mars. When we are presented with a complex problem depending on a great number of imperfectly ascertained data, we may often check the results thus obtained with the comparison of cases which in some of the more important of these data are identical, while others are at a maximum or a minimum. In the present case, we can only do this by a consideration of the Moon as compared with the Earth and with Mars. Langley's determination of the Moon's temperature. In the Moon, we see conditions that prevail in Mars, both exaggerated and simplified. Mars has a very scanty atmosphere, the Moon none at all. Or if there is one, it is so excessively scanty that the most refined observations have not detected it. All the complications arising from the possible nature of the atmosphere and its complex effects upon reflection, absorption, and radiation are thus eliminated. The mean distance of the Moon from the Sun being identical with that of the Earth, the total amount of heat intercepted must also be identical. Only in this case, the whole of it reaches the surface instead of 1/4 only, according to Mr. Lowell's estimate for the Earth. Now, by the most refined observations with his bolometer, Mr. Langley was able to determine the temperature of the Moon's surface exposed to undimmed sunshine for 14 days altogether. And he found that even in the portion of it on which the sun was shining almost vertically, the temperature rarely rose above the freezing point of water. However extraordinary this result may seem, it is really a striking confirmation of the accuracy of the general laws determining temperature which I have endeavored to explain in the preceding chapter. For the same surface, which has had 14 days of sunshine, has also had preceding 14 days of darkness, during which the heat which it had accumulated in its surface layers would have been lost by free radiation into stellar space. It thus acquires during its day a maximum temperature of only 491 degrees Fahrenheit absolute, while its minimum, after 14 days continuous radiation, must be very low and is, with much reason, supposed to approach the absolute zero. Rapid loss of heat by radiation on the Earth. In order better to comprehend what this minimum may be under extreme conditions, it will be useful to take note of the effects it already produces on the Earth in places where the conditions are nearest to those existing on the Moon or on Mars. Though never quite equaling or even approaching very near them, it is in our great desert regions, and especially on high plateaux, that extreme aridity prevails, and it is in such districts that the differences between day and night temperatures reach their maximum. It is stated by geographers that in parts of the Great Sahara the surface temperature is sometimes 150 degrees Fahrenheit, while during the night it falls nearly or quite to the freezing point, a difference of 118 degrees in little more than 12 hours. See footnote 10. In the high desert plains of Central Asia, the extremes are said to be even greater. See footnote 11. Again, in his Universal Geography, Reckless states that in the Armenian highlands the thermometer oscillates between 13 degrees Fahrenheit and 112 degrees Fahrenheit. We may therefore, without any fear of exaggeration, take it as proved that a fall of 100 degrees Fahrenheit in 12 or 15 hours not unfrequently occurs where there is a very dry and clear atmosphere, permitting continuous insolation by day and rapid radiation by night. Now, as it is admitted that our dense atmosphere, however dry and clear, absorbs and reflects some considerable portion of the solar heat, we shall certainly underestimate the radiation from the Moon's surface during its long night if we take as a basis of our calculation a lowering of temperature amounting to 100 degrees Fahrenheit during 12 hours, as not unfrequently occurs with us. Using these data, with Stephan's law of decrease of radiation as the fourth power of the temperature, a mathematical friend finds that the temperature of the moon's surface will be reduced during the lunar night to nearly 200 degrees Fahrenheit absolute, equal to minus 258 degrees Fahrenheit. More rapid loss of heat by the moon. Although such a calculation as the above may afford us a good approximation to the rate of loss of heat by Mars with its very scanty atmosphere, we have now good evidence that in the case of the moon the loss is much more rapid. Two independent workers have investigated the subject with very accordant results. Dr. Bodecker, with Lord Rosse's 3-foot reflector and a thermopile to measure the heat, and Mr. Frank Very with a glass reflector of 12 inches in diameter and the bolometer invented by Mr. Langley. The very striking and unexpected fact in which these observers agree is the sudden disappearance of much of the stored up heat during the comparatively short duration of a total eclipse of the moon. Less than 2 hours of complete darkness and about twice that period of partial obscuration. Dr. Bodecker was unable to detect any appreciable heat at the period of greatest obscuration, but owing to the extreme sensitiveness of the bolometer, Mr. Very ascertained that those parts of the surface which had been longest in shadow still emitted heat to the amount of 1% of the heat to be expected from a full moon. This, however, is the amount of radiation registered by the bolometer. And to get the temperature of the radiating surface, we must apply Stephan's law of the fourth power. Hence, the temperature of the moon's dark surface will be the fourth root of 1 over 100, equivalent to 1 over 3.2 of the highest temperature, which we may take at the freezing point of 491 degrees Fahrenheit absolute, or 154 degrees Fahrenheit absolute, just below the liquefaction point of air. This is about 50 degrees lower than the amount found by calculation from a most rapid radiation, and this amount is produced in a few hours. It is not too much to expect that when continued for more than 2 weeks, the lunar night, it might reach a temperature sufficient to liquefy hydrogen, 60 degrees Fahrenheit absolute, or perhaps even below it. Theory of the moon's origin. This extremely rapid loss of heat by radiation, at first sight so improbable as to be almost incredible, may perhaps be to some extent explained by the physical constitution of the moon's surface, which from a theoretical point of view does not appear to have received the attention it deserves. It is clear that our satellite has long been subjected to volcanic eruptions over its whole visible face, and these have evidently been of an explosive nature, so as to build up the very lofty cones and craters as well as thousands of smaller ones which, owing to the absence of any degrading or denuding agencies, have remained piled up as they were first formed. This highly volcanic structure can, I think, be well explained by an origin such as that attributed to it by Sir George Darwin, and which has been so well described by Sir Robert Ball in his small volume Time and Tide. These astronomers adduce strong evidence that the earth once rotated so rapidly that the equatorial protuberance was almost at the point of separation from the planet as a ring. Before this occurred, however, the tension was so great that one large portion of the protuberance, where it was weakest, broke away and began to move around the earth at some considerable distance from it. As about 1/50th of the bulk of the earth thus escaped, it must have consisted of a considerable portion of the solid crust and a much larger quantity of the liquid or semi-liquid interior, together with a proportionate amount of the gases which we know formed and still form an important part of the earth's substance. As the surface layers of the earth must have been the lightest, they would necessarily, when broken up by the gigantic convulsion, have come together to form the exterior of the new satellite, and soon be adjusted by the forces of gravity and tidal disturbance into a more or less irregular spheroidal form, all of whose interstices and cavities would be filled up and connected together by the liquid or semi-liquid mass forced up between them. Thenceforward, as the moon increased its distance and reduced its time of rotation in the way explained by Sir Robert Ball, there would necessarily commence a process of escape of the imprisoned gases at every fissure and at all points and lines of weakness, giving rise to numerous volcanic outlets, which, being subjected only to the small force of lunar gravity, only 1/6 that of the earth, would in the course of ages pile up those gigantic cones and ridges which form its great characteristic. But this small gravitative power of the moon would prevent its retaining on its surface any of the gases forming our atmosphere, which would all escape from it and probably be recaptured by the earth. By no process of external aggregation of solid matter to such a relatively small amount as that forming the moon, even if the aggregation was so violent as to produce heat enough to cause liquefaction, could any such long-continued volcanic action arise by gradual cooling in the absence of internal gases. There might be fissures and even some outflows of molten rock, but without imprisoned gases, and especially without water and water vapor producing explosive outbursts, could any such amount of scoriae and ashes be produced as were necessary for the building up of the vast volcanic cones, craters, and craterlets we see upon the moon's surface. I am not aware that either Sir Robert Ball or Sir George Darwin have reduced this highly volcanic condition of the moon's surface as a phenomenon which can only be explained by our satellite having been thrown off by a much larger body, whose gravitative force was sufficient to acquire and retain the enormous quantity of gases and of water which we possess, and which are absolutely essential for that special form of cone-building volcanic action which the moon exhibits in so pre-eminent a degree. Yet it seems clear to me that some such hypothetical origin for our satellite would have had to be assumed if Sir George Darwin had not deduced it by means of purely mathematical argument based upon astronomical facts. Returning now to the problem of the moon's temperature, I think the phenomena this presents may be in part due to the mode of formation here described, for its entire surface being the result of long-continued gaseous explosions, all the volcanic products, scoriae, pumice, and ashes, would necessarily be highly porous throughout, and never having been compacted by water action as on the earth, and there having been no winds to carry the finer dust so as to fill up their pores and fissures, the whole of the surface material, to a very considerable depth, must be loose and porous to a high degree. This condition has been further increased owing to the small power of gravity and the extreme irregularity of the surface, consisting very largely of lofty cones and ridges very loosely piled up to enormous heights. Now this condition of the substances of the moon's surface is such as would produce a high specific heat, so that it would absorb a large amount of heat in proportion to the rise of the temperature produced, the heat being conducted downwards to a considerable depth. Owing, however, to the total absence of atmosphere, radiation would very rapidly cool the surface, but afterwards more slowly, both on account of the action of Stephan's law and because the heat stored up in the deeper portions could be carried to the surface by conduction only, and with extreme slowness. Various researches on the moon's heat. The results of the eclipse observations are supported by the detailed examination of the surface temperature of the moon by Mr. Very in his prize essay on the distribution of the moon's heat, published by the Utrecht Society of Arts and Sciences in 1891. He shows by a diagram of the phase curve that at the commencement of the lunar day the surface just within the illuminated limb has acquired about 1/7 of its maximum temperature, or about 70 degrees Fahrenheit absolute. As the surface exposed to the bolometer at each observation is about 1/30th of the moon's surface, and in order to ensure accuracy, the instrument has to be directed at a spot lying wholly within the edge of the moon. It is evident that the surface measured has already been for several hours exposed to oblique sunshine. The curve of the temperature then rises gradually and afterwards more rapidly, till it attains its maximum of about positive 30 to 40 degrees Fahrenheit a few hours before noon. This, Mr. Very thinks, is due to the fact that half the moon's face first illuminated for us has on the average a darker surface than that of the afternoon or second quarter, during which the curve descends not quite so rapidly, the temperature near sunset being only a little higher than that near sunrise. This rapid fall while exposed to oblique sunshine is quite in harmony with the rapid loss of heat during the few hours of darkness during an eclipse, both showing the prepotency of radiation over insolation on the moon. Two other diagrams show the distribution of heat at the time of full moon, one half of the curve showing the temperatures along the equator from the edge to the disk of the center, the other along a meridian from this center to the pole. This diagram, here reproduced, exhibits the quick rise of temperature of the oblique rim of the moon and the nearly uniform heat of the central half of its surface. The diminution of heat towards the pole, however, is slower for the first half and more rapid for the latter portion. It is an interesting fact that the temperature near the margin of the full moon increases towards the center more rapidly than it does when the same parts are observed during the early phases of the first quarter. Mr. Very explains this difference as being due to the fact that the full moon to its very edges is fully illuminated, all of the shadows of the ridges and mountains being thrown vertically or obliquely behind them. We thus measure the heat reflected from the whole visible surface. But at new moon, and somewhat beyond the first quarter, the deep shadows thrown by the smallest cones and ridges, as well as the loftiest mountains, cover a considerable portion of the visible surface, thus largely reducing the quantity of light and heat reflected or radiated in our direction. It is only at the full, therefore, that the maximum temperature of the whole lunar surface can be measured. It must be considered a proof of the delicacy of the heat-measuring instruments that this difference in the curves of temperature of the different parts of the moon's surface and under different conditions is so clearly shown. The application of the preceding results to the case of Mars. This somewhat lengthy account of the actual state of the moon's surface and temperature is of very great importance in our present inquiry, because it shows us the extraordinary differences in mean and extreme temperature of two bodies situated at the same distance from the sun, and therefore receiving exactly the same amount of solar heat per unit of surface. We have learned also what are the main causes of this almost incredible difference, namely, 1. A remarkably rugged surface with porous and probably cavernous rock texture, leading to an extremely rapid radiation of heat in the one as compared with a comparatively even and well-compacted surface largely clad with vegetation, leading to a comparatively slow and gradual loss by radiation in the other. And 2. These results being greatly intensified by the total absence of a protecting atmosphere on the former, while a dense and cloudy atmosphere with an ever-present supply of water vapor accumulates and equalizes the heat received by the latter. The only other essential difference in the two bodies which may possibly aid in the production of this marvelous result is the fact of our day and night having a mean length of 12 hours, while those of the moon are about 14.5 of our days. But the altogether unexpected fact, in which two independent inquirers agree, that during the few hours' duration of a total eclipse of the moon, so large a portion of the heat is lost by radiation, renders it almost certain that the resulting low temperature would be not very much less if the moon had a day and night the same length as our own. The great lesson we learn by this extreme contrast of conditions supplied to us by nature as if to enable us to solve some of her problems is the overwhelming importance, first, of a dense and well-compacted surface, due to water action and strong gravitative force. Secondly, of a more or less general coat of vegetation. And thirdly, of a dense, vapor-laden atmosphere. These three favorable conditions result in a mean temperature of about 60 degrees Fahrenheit, with a range seldom exceeding 40 degrees above or below, while over more than half of the land surface of the Earth, the temperature rarely falls below the freezing point. On the other hand, we have a globe with the same materials and at the same distance from the sun, with a maximum temperature of freezing water, and a minimum not very far from the absolute zero. The monthly mean being probably much below the freezing point of carbonic acid gas, a difference entirely due to the absence of these three favorable conditions. The special features of Mars as influencing temperature. Coming now to the special feature of Mars and its probable temperature, we find that most writers have arrived at a very different conclusion from that of Mr. Lowell, who himself quotes Mr. Moulton as an authority, who recently, by the application of Stephan's law, has found the mean temperature of this planet to be minus 35 degrees Fahrenheit. Again, Professor J. H. Poynting, in his lecture on radiation in the solar system, delivered before the British Association at Cambridge in 1904, gave an estimate of the mean temperature of the planets, arrived at from measurements of the sun's emissive power and the application of Stephan's law to the distances of the several planets. And he thus finds the Earth to have a mean temperature of 17 degrees centigrade, and Mars to have one of minus 38 degrees centigrade. A wonderfully close approximation to the mean temperature of the Earth as determined by direct measurement, and therefore, presumably, an equally near approximation to that of Mars is dependent on the distance from the Sun, and on the supposition that it is Earth-like in all its conditions. But we know that it is far from being Earth-like in the very conditions which we have found to be those which determine the extremely different temperatures of the Earth and Moon, and in regards to each of these, we find that so far as it differs from the Earth, it approximates to the less favorable conditions that prevail in the Moon. The first of these conditions which we have found to be essential in regulating the absorption and radiation of heat, and thus raising the mean temperature of a planet, is a compact surface well covered with vegetation, two conditions arising from and absolutely dependent on an ample amount of water. But Mr. Lowell himself assures us, as a fact which he has no doubt, that there are no permanent bodies of water, great or small, upon Mars, that rain and consequently rivers are totally wanting, that its sky is almost constantly clear, and that what appear to be clouds are not formed of water vapor, but of dust. He dwells emphatically on the terrible desert conditions of the greater part of the surface of the planet. That being the case now, we have the right to assume that it has ever been otherwise, and, taking into full account of the fact, neither denied nor disputed by Mr. Lowell, that the force of gravity on Mars is not sufficient to retain water vapor in its atmosphere, we must conclude that the surface of the planet, like that of the Moon, has been molded by some form of volcanic action, modified probably by wind, but not by water. Adding to this, that the force of gravity on Mars is nearer that of the Moon than that of the Earth, we may reasonably conclude that its surface is formed of volcanic matter and a light porous condition, and therefore highly favorable for the rapid loss of surface heat by radiation. The surface conditions of Mars are therefore presumably much more like those of the Moon than those of the Earth. The next condition favorable to the storing up of heat, a covering of vegetation, is almost certainly absent from Mars, except possibly over limited areas and for short periods. In this feature, also the surface of Mars approximates much nearer to the lunar than to Earth conditions. The third condition, a dense vapor-laden atmosphere, is also wanting in Mars, for although it possesses an atmosphere, it is estimated by Mr. Lowell in his latest article to have a pressure equivalent to only 2½ inches of mercury with us, giving it a density of only 1/12 part that of ours, while aqueous vapor, the chief accumulator of heat, cannot permanently exist in it, and notwithstanding repeated spectroscopic observations for the purpose of detecting it, has never been proved to exist. I submit that I have now shown from the statements, and largely as a result of the long-continued observations by Mr. Lowell himself, So far as the physical conditions of Mars are known to differ from those of Earth, the differences are all unfavorable to the conservation and favorable to the dissipation of the scanty heat it receives from the sun, that they point unmistakably toward the temperatures conditions of the moon rather than to those of the earth, and that the cumulative effect of these adverse conditions acting upon the heat supply reduced by solar distance to less than 1/2 of ours must result in a mean temperature, as well as in the extremes nearer to that of our satellite than to that of our own Earth. Further criticism of Mr. Lowell's article. We are now in a position to test some further conclusions of Mr. Lowell's Philosophical Magazine article by comparison with actual phenomena. We have seen in the outline I have given of this article that he endeavors to show how the small amount of solar heat received by Mars is counterbalanced largely by the greater transparency to light and heat of its thin and cloudless atmosphere, and partially also by a greater conservative or blanketing power of its atmosphere due to the presence in it of a large proportion of carbonic acid gas and aqueous vapor. The first of these statements may be admitted as a fact which is entitled to dwell upon, but the second, the presence of large quantities of carbon dioxide and aqueous vapor, is a pure hypothesis, unsupported by any item of scientific evidence. While in the case of aqueous vapor, it is directly opposed to admitted results founded upon the molecular theory of gaseous elasticity. But although Mr. Lowell refers to the conservative or blanketing effect of the Earth's atmosphere, he does not consider or allow for its very great cumulative effect, as is strikingly shown by the comparison with the actual temperature conditions of the moon. This cumulative effect is due to the continuous reflection and radiation of heat from the clouds as well as from the vapor-laden strata of air in our lower atmosphere, which latter, though very transparent to the luminous and accompanying heat rays of the sun, is opaque to the dark heat rays whether radiated or reflected from the Earth's surface. We are therefore in a position strictly comparable with that of the interior of some huge glass house, which not only becomes intensely heated by the direct rays of the sun, but also to a less degree by reflected rays from the sky and those radiated from the clouds, so that even on a cloudy or misty day its temperature rises many degrees above that of the outer air. Such a building, if of large size, of suitable form, and well protected at night by blinds or other covering, might be so arranged as to accumulate heat in its soil and walls as to maintain a tolerably uniform temperature, though exposed to a considerable range of external heat and cold. It is to such a power of accumulation of heat in our soil and lower atmosphere that we must impute the overwhelming contrast between our climate and that of the moon. With us, the solar heat that penetrates our vapor-laden and cloudy atmosphere is shut in by that same atmosphere, accumulates there for weeks and months together, and can only slowly escape. It is this great cumulative power which Mr. Lowell has not taken account of, while he certainly has not estimated the enormous loss of heat by free radiation which entirely neutralizes the effects of increase of sun heat, however great, when these cumulative agencies are not present. See footnote 12. Temperature on polar regions of Mars. There is also a further consideration which I think Mr. Lowell has altogether omitted to discuss. Whatever may be the mean temperature of Mars, we must take account of the long nights in its polar and high-temperate latitudes, lasting nearly twice as long as ours, with the resultant lowering of temperature by radiation into a constantly clear sky. Even in Siberia, in latitude 67.5 degrees north, a cold of minus 88 degrees Fahrenheit has been attained, while over a large portion of North Asia and America above 60 degrees latitude, the mean January temperature is from minus 30 degrees Fahrenheit to minus 60 degrees Fahrenheit, and the whole subsoil is permanently frozen to a depth of 6 or 7 feet to several hundreds. But the winter temperature over the same latitudes in Mars must be very much lower, and it must require a proportionally larger amount of its feeble sun heat to raise the temperature even to the freezing point, and an additional very large amount to melt any considerable depth of snow. But this identical area, from a little below 60 degrees to the pole, is that occupied by the snow caps of Mars, and over the whole of it the winter temperature must be far lower than the Earth minimum of minus 88 degrees Fahrenheit. Then, as the Martian summer comes on, there is less than half the sun heat available to raise this low temperature after a winter nearly double the length of ours. And when the summer does come with its scanty sun heat, that heat is not accumulated as it is by our dense and moisture-laden atmosphere, the marvelous effects of which we have already shown. Yet with all these adverse conditions, each assisting the other to produce a climate approximating to that which the earth would have if it had no atmosphere, but retaining our superiority over Mars in receiving double the amount of sun heat, we are asked to accept a mean temperature for the more distant planet almost exactly the same as that of mild and equable southern England, and the disappearance of the vast snowfields of its polar regions as rapid and complete as what occurs with us. If the moon, even at its equator, had not its temperature raised above the freezing point of water, how can the more distant Mars, with its oblique noonday sun falling upon the snow-caps, receive heat enough first to raise the temperature to 32 degrees Fahrenheit, and then to melt with marked rapidity the vast frozen plains of its polar regions? Mr. Lowell is, however, so regardless of the ordinary teachings of meteorological science that he actually accounts for the supposed mild climate of the polar regions of Mars by the absence of water on its surface and in its atmosphere. He concludes in his 5th chapter with the following words: "Could our Earth but get rid of its oceans, we too might have temperate regions stretching to the poles." Here he runs counter to two of the best established laws of terrestrial climatology: the wonderful equalizing effects of warm ocean currents, which are the chief agents in diminishing polar cold, the equally striking effects of warm, moist winds derived from these oceans, and the great storehouse of heat we possess in our vapor-laden atmosphere, its vapor being primarily derived from these same oceans. But in Mr. Lowell's opinion, all our meteorologists are quite mistaken. Our oceans are our great drawbacks. Only get rid of them, and we should enjoy the exquisite climate of Mars, with its absence of clouds and fog, of rains or rivers, and its delightful expanses of perennial deserts, varied towards the pole by a scanty snowfall in winter, the melting of which might, with great care, supply us with the necessary moisture to grow wheat and cabbages for about 1/10, or more likely 1/100th of our present population. I hope I may be excused for not treating such an argument seriously. The various considerations now advanced, especially those of which show the enormous cumulative and conservative effect of our dense and water-laden atmosphere, and the disastrous effect, judging from the actual condition of the moon, which the loss of it would have upon our temperature, seem to me quite sufficient to demonstrate important errors in the data, or fallacies in the complex mathematical argument by which Mr. Lowell has attempted to uphold his views as to the temperature and consequent climatic conditions of Mars. In concluding this portion of my discussion of the problem of Mars, I wish to call attention to the fact that my arguments, founded upon a comparison of the physical conditions of the Earth and Moon with those of Mars, is dependent on a small number of generally admitted scientific facts, while the conclusions drawn from those facts are simple and direct, requiring no mathematical knowledge to follow them or to appreciate their weight and cogency. I claim for them, therefore, that they are in no degree speculative, but in their data and methods exclusively scientific. In the next chapter I will put forth a suggestion as to how the very curious markings upon the surface of Mars may possibly be interpreted, so as to be in harmony with the planet's actual physical condition and its not improbable origin and past history. Footnote 10. Keith Johnston's Africa in Stanford's Compendium. Footnote 11. Chambers' Encyclopedia, article on deserts. Footnote 12. The effects of this cumulative power of a dense atmosphere are further discussed and illustrated in the last chapter of this book, where I show that the universal fact of steadily diminishing temperatures at higher altitudes is due solely to the diminution of this cumulative power of our atmosphere, and that from this cause alone the temperatures of Mars must be at that which would be found on the lofty plateau about 18,000 feet higher than the average peaks of the Andes. This concludes Chapter 6.